hello everyone. In this presentation, we're going to be talking about some improvements to generative design that have made this incredible technology more usable than ever before. Generative design is a revolution unto itself, and we're very fortunate to be witnessing the enormous effect that it's having on part design. Clearly, every industry is going to be benefiting from this technology in years to come. And the technology allows you to make parts both lighter and stronger at the same time. It's just amazing. And today, SolidCAD's very own Dan Lodpath-Montanu, engineer and simulation expert, is going to have fun telling us how we can now ask generative design to come up all on its own with parts that aren't just only high performance, but also easy to manufacture. So I just want to say, as with all the other presentations at our virtual expo, this presentation is live and you're encouraged to submit your questions in real time and to vote on other people's questions. Dan will have 15 minutes at the end of the presentation to address these questions. So take it away, Lodpath.
Thank you, Louis. Let me share my screen here. Can you see this okay?
Yep.
Alrighty. And I hope you can hear me okay too. My microphone slides away sometimes. Okay, so yeah, thank you everyone for joining this later afternoon session. Another one coming after this. I hope you found these 2 days informative, and you'll find new ways of improving your processes. So this talk is about generative design in general, and its specific application to manufacturing processes. Our coordinates are on screen here if you need to contact us later on. So my plan for the next 20-30 minutes is to walk you through the Autodesk implementation of generative design and look at a workflow with Fusion 360. And hopefully you'll find this interesting enough to ask plenty of questions at the end. Without going too far back the memory lane here, and recognizing the technology advancements in the last 40, 50 years, here's a bit of a half funny slide here showing us the evolution of a design engineering team from drafting boards and plenty of paper and pen to some of the earlier versions of AutoCAD 1.4 running on an Intel 286 with a mathematical coprocessor chip, the famous 287, which if you did not have, you could actually run a software coprocessor, mathematical coprocessor, much slower. All the way to current times of Inventor 3D parametric modeling. And I guess the question is, what's next? What is going to be the next revolution that Harvard Business Review named once the next wave of intelligent design automation? The traditional optimization methods are pretty straightforward. You take a known solution, you do some simulation and testing, so either virtual or physical analysis to confirm design validity. Chances are changes are going to be required, so more CAD modeling, and you'll go back to the first step. Iterate on this and spend more time trying to chase that ideal solution. We have been doing this for 30 years at least, in parametric solid modeling. Newer techniques like topology optimization are already in place, and for those of you who are Autodesk Inventor users. You recognize these pictures on screen. It's the shape generator in the inventor stress analysis. So nothing wrong with this. It's just that we are going to obtain one solution which depends a lot on the starting shape. So it's a technique that simply removes material outside of the load path and has usually a single goal, a single design objective. So moving from here to the generative design, we're not just optimizing at that point. We're actually exploring design alternatives, and we can only do this because of the newest artificial intelligence and machine learning algorithms that have been developed quite recently. So this Autodesk generative design solution is cloud-enabled, powered by the Amazon Web Services and NVIDIA. It's using different, let's call them services, EC2, P3 for GPU computing from Amazon, the storage S3, and the machine learning, the famous Amazon SageMaker. And the advantage here is we're getting viable outcomes presented to the user at the same time. So multiple solutions, and this explorative approach is it's multi-goal driven. So it's a multi-goal optimization process. And the users can do various trade-offs for performance. I mean, there's lightweighting in place here, obviously, but the critical aspect compared to the classical, if you want, topology optimization is the manufacturability of the parts. So different manufacturing techniques are going to be available, as you'll see shortly, and this will allow us to create parts which are ready to go, ready to be produced. So without again going back too far in history here, it was a project started at Autodesk Research and their AI lab. University of Toronto had a big contribution there. There were researchers in London, in San Francisco. They developed what used to be known as a project Dreamcatcher a few years back, and it's this technology. It's out in the open. Is not a preview. Is not in beta testing. It's currently being used by customers all over the world. On the manufacturing space, we have an implementation in Fusion 360, and there are newer approaches of the technique that are starting to become available in other industries like AC, currently available in Revit 2021. So what is generative design, in case this term is relatively new to you? It's as I said, a multi-goal optimization procedure that enables these artificial intelligence algorithms to search for optimum criteria based on optimum solutions based on multi-goal criteria. And there are some clear benefits to engineers in terms of being able to look at multiple solutions, so improving product performance, picking up the best of the results, increasing product innovation, allowing you to look at multiple alternatives, design shapes that are otherwise even hard to imagine, and not in the last respect, reducing product cost. So improving performance while reducing cost, which is kind of like the holy grail here of design. If you want to learn more about this, there's a link at the bottom of the slide there to an ebook by Autodesk. I encourage you to download and read. Now, I mentioned the GD implementation for manufacturing is in Fusion 360. So I'm sure most of you have heard of Fusion 360. If not, hopefully this slide will spark your curiosity to run a quick Google search and read more about it on the Autodesk website. So a cloud-based platform, multidisciplinary, with collaboration and in the forefront. Anything from 3D parametric and direct solid modeling, surface modeling, electronics design, so printed circuit board, rapid prototyping, manufacturing workspace, collaboration, the stress and more newly computation fluid dynamics analysis, as well as not in the list here, generative design. Definitely a platform that you want to know, you want to get to know better and think where you can fit in your design process. So the GD, generative design implementation in Fusion 360, it will let you generate multiple CAD-ready designs with the real-world manufacturing constraints based on the performance goals that you have added there. So multiple outcomes is the important aspect here. You're going to be able to explore hundreds, if not thousands, of design variations and pick the ones that are most suitable to you. Traditionally, the generative design is considered a tool, a shape generation tool that produced what I guess half-jokingly were called alien parts. Maybe some of you are science fiction fans. I guess what comes to my mind is Ender's Game, the movie where the Formix planet was described. Anyway, alien parts through and through. But the latest updates of generative design, and by latest I mean about a year already, which in Fusion 360 updates term is probably, I'm going to say, at least 6 updates that have happened. So the latest updates allow for actually an implementation based on traditional manufacturing methods. So subtractive manufacturing methods based on 2-axis cutting, water jet, plasma cutting, or milling are now available for your selection. So these manufacturing methods are going to be considered through and through when these algorithms try to generate the shape. So 2.5, 3-axis, and even 5-axis milling, as well as die casting. Additive manufacturing, still a very important aspect of the generative design. Once you really want to go, organic shapes and free form, that is probably the only way you can achieve some of these. So if you're to consider these advantages of a generative design process, being able to operate with multiple materials and create shapes which have specific strength constraints, cost constraints, mass constraints, and being able to operate within a set of real-life materials, manufacturable type materials. It's going to be important here. All in the context of trying to reduce that time to market. Here's an example from a Fusion 360 and Generative Design early adopters, MJK Performance in Calgary. They produce high-end aftermarket parts for Harley Davidson motorcycles. So here's an example of this triple clamp parts where a human design was improved by a weight reduction within still a specified safety factor. Being able to produce these parts using 2.5 and 3-axis milling. Another aspect that I wanted to mention here before we get into the tool, I promise I won't be boring you more with slides, is the fact that we're actually able to look at true manufacturing cost and have that information right away when you make a design decision. So this is through a partnership with a Priori. They produce a leading design and manufacturing design for manufacturability and cost tool that uses these large databases of materials and processes and manufacturing data, tolerances, and so on, to be able to estimate accurately the cost per part for a certain production volume. So you're trying here to get to the right balance of manufacturing cost, production volume, material cost, and so on. So let's look at the generative design process, the step-by-step process in Fusion 360. It is pretty straightforward, like pretty much Fusion 360 is in terms of interface and workflow. Let's say four let's say major steps until you get to actually use the part in your own assembly. So we start with a setup in a design space. We go for an exploration of the outcomes, so-called, and we take that in the 3D model and validate it. So I'm going to jump into my Fusion 360 here. I hope you can still see my screen here. All right. So we're gonna walk through a simple example similar to the MJK Performance triple clamp. We have here a motorcycle model, courtesy of Autodesk. Thank you. And we're going to take. Actually, before we go any further, let me just jump back to my slide here for a second. So I should have maybe shown you this first. So we're going to start by defining the goal, isolating the relevant components that we're going to look to improve, optimize. We're going to take those into a workspace in Fusion called the Generative Design workspace. We're going to look at some simple geometry creation, and the important part here is going to be to define what they're known as the preserve geometry. So keep in, do not modify, do not delete, do not change. Specifically, these are going to allow us to maintain connections with other components in our assembly, as well as the so-called obstacle geometry, and you can see how they're color coded there, easy to figure things out. So the obstacle geometry will be parts and or volumes that are going to be avoided, so the so-called keep out. So let's see how we do these steps. We're going to start by selecting the components here. So let's go grab these, right? So we can isolate these, and that will allow us to hide everything. Or we can simply take those and copy paste them into a new design, right? So I could also do this and just paste as new, right click into a new design here, and let's just take a look. So we know we're going to want to connect with these two struts. This is the current design. Let's see if we get artificial intelligence algorithms to generate something different. And we're going to go to the Generative Design workspace now. So in the Generative Design workspace, we have this opportunity of creating now some additional geometry that we will use as preserves and as well as keep out. So for example, just to for those of you who maybe have not seen Fusion before, so if I'm going to jump into the edit model here, if I'm to create a sketch on this face and maybe project some geometry and let's say offset that projected geometry, which was here, a certain amount, right? So I could take that. Let's do the same here. I could take that and use it as a sketch to be able to create my point. Let's say 8.5, right? To create my preserve regions here. So these are going to become now new bodies, new solid bodies. So I'm selecting these. I'm creating a solid body of a certain height. So a typical parametric solid modeling. The advantage, though, is the fact that I'm doing this in the context of my generative design environment. So why is this important? Well, it's important because it actually does not affect my other design, my overall components. The sketch got hidden here, so let me just go back and turn it on. Some preferences which you can tweak. So I could go and say to this depth, right? The software switches to cut because it detects more solids there. I'm just going to create that. So this allows me, as I said, to use some of this geometry as preserve on and define it as such here. So I'm going to go and say this is going to be geometry to be preserved. In other words, I want to preserve that internal diameter. I don't want generative design to add material there or maybe somehow create a shape that will not allow these struts to fit in. So that's my preserved geometry. And now I'm selecting the obstacle geometry. So for obstacle geometry, I could go and select these two, okay? And I also have, and that's an option. You could choose to skip this. You could start with a starting shape. So if you want to, let's say, improve on this, you could choose this as a starting shape, right? That's also going to be allowed to be defined here. Now, this starting shape, in fact, if I am to maybe unselect it, could also be simplified. So I could go and say, edit the model. Here it is. And I'm back into editing model, which again will not affect the original body. What can I do here? Well, I could actually go and maybe remove some of the fillets and chamfers, and so you're trying to get to a simpler shape to maybe allow this generative design strategy to figure out an easier solution, reduce the complications if you want. Okay, so I'm doing a so-called defeaturing by removing fillets and chamfers of different sizes. You could also use remove face, for example. So if I go and select that and click delete, right? So you're basically simplifying the model enough to allow you to define that as what is this in this case, a starting shape. Now, so once you have all these defined, you are going to, let me just jump to a slide here. You're going to define the objectives and the limits. And this is an important part. It will tell the algorithms what is the goal. What am I trying to get to here? The options are minimize the mass or maximize the stiffness in the context of a target mass. Go for a certain target safety factor. And as I mentioned earlier, Fusion 360 goes through many updates, and the technology keeps on improving. There are some options there for you to turn on if you want to explore. So they're provided as a technology preview now, and they won't be visible unless you do turn them on. Will also allow me to define a maximum displacement and a specific modal frequency as my goals. Why would this be important? Well, maybe I can't allow this part to deflect more than a certain amount, because maybe it's in a tight space. It will go in contact with some other components, wear and so on problems. Or maybe it's in a vibratory environment, and I'm trying to get this to avoid certain frequencies. So my component should have natural frequencies and mode shapes outside of a certain range. So as you can probably imagine at this point, by adding these constraints, as you'll also get to see here, by creating the so-called load cases, loads and constraints, we'll come back to this. We're actually asking the software to do many calculations. So there'll be linear static analysis or model analysis run on every single design iteration that the software produces. Clearly, something like this is not possible unless you use some cloud computing capabilities. This will not run on my laptop or on your desktop. So cloud solving only. So let's go back here, and I'm actually going to jump on my model here, where I cleaned up a little bit more. So here's my starting shape. So what I did here is go and create these as design objectives. So minimize the mass and create a target safety factor of 2. So here's the other option with a mass target, as well as define the manufacturing methods. So this is the critical part, and the subject of eventually, we did get to the crux of the matter. Sorry, looks like I'm starting to be short on time here.
Okay,
So
Dan,
yes.
we're cutting into the question period. It's okay, keep going, because
Yeah.
you are getting to the sexy stuff here. So
Well, this is the important part. Sorry.
yep, please go ahead. Yeah.
Yeah. So what we're doing here is we're telling the software to look for solutions that are actually viable, that can be created, and the methods are going to be based on your settings here. And this is something you can choose to select or not, based on what is it you have access to, right? So if you don't have a 5-axis machine, well, you're not going to define a 5-axis configuration here. Unrestricted, what it means really is the perfect shape. You just let the algorithms run wild if you want. It'll get you to the minimum mass, something that might be a bit pie in the sky and unachievable. Once you get into specific manufacturing methods like additive manufacturing, then you get to say, okay, well, what is the axis I'm going to use? This part is going to sit on the platform in a certain way, in a certain orientation. What would be the maximum overhang angle past which the amount of supports might not be feasible to to be allowed. So you're getting into very specific things. So in terms of milling, I have up to 4 configurations here: 2.5, 3 axis, and 5 axis. On each of them, I could say what is the axis direction to the part, and I have capabilities in terms of what would be the tool properties that will be able to reach to, that areas on that part. So I will say the smallest tool that I'm using is 1/8 of an inch, for example, and the tool shoulder length is. So the software will generate these shapes trying to fit this criteria. Okay. Same for 2.5 axis, minimum tool diameter and minimum wall thickness, as well as the on the 5 axis head diameter and shoulder length, as well as again minimum tool diameter. 2 axis cutting, same thing, minimum wall thickness, and the direction, the approach direction. And for die casting, if I would be to choose that, there would be the ejection direction. So let's say this would be this Y in this case, minimum draft angle, minimum thickness, and so on. So this is going to be critical. Also, the production volume here up top, how many parts I'm going to want to produce, will be important to give me a cost estimate per part. So once you set this up, you're now ready to start defining materials, right? So sorry, I should have gone to this part right here, materials. And you have up to 7 materials per manufacturing process to choose from. Plenty of materials in the library here with cost information. And at that point, you're starting to really look into the details of, if I'm going to have a milling operation or a milling process here, what are my options in terms of real materials that I could use, and so on. And lastly, what you have is the ability of loading the part. Remember, I had earlier a safety factor that I was looking at. Well, this is in the context of some linear static analysis that the software will run for each iteration to be able to give you the to be able to let you set up the loads that you're applying to the part. So in this case, I'm I'm applying, if I'm to maybe switch this to wireframe. So I'm applying some loads in the, let's see here. Right, so opposite direction, pretty much arbitrary direction there to twist this part around x-axis direction, as well as a set of bending loads that will bend this about z-axis. And I'm also holding the part, so there's a fixed constraint in the center. So you're coming up with what kind of loads my part will take, will need to be able to support, and the conditions based on those materials in terms of safety factor, maximum displacement, and so on. So when this is ready, you have the option to do a preview here. See if you set everything up, the software will start to kind of generate a basic shape. And if that looks okay, then you can hit the generate button. This gets sent to the cloud fast, and then the calculation process starts. And depending on how many conditions and materials and how complicated the geometry is and how many preserves and obstacles you have, this can take a few hours. So once you're ready, let me just jump to the outcome here. So what happens here is, actually, before we go there, let me just go back to this. I'll hit explore button. This is the exploration phase. So you are now in the let's say the happy owner of many thousands of different options and variants. And we have this very nice tool as a scatter plot to be able to start exploring the results. So I'm looking at all sorts of outputs, let's say formicis stress versus mass, right? Or minimum safety factor versus mass. So you're exploring now all these variants, zoom in and figure out which one is the one that actually makes the most sense to you, right? And as well as you get some cost information here, as well as the manufacturing method. You can also do some comparison. So I could go and, let's say, isolate the 2.5 axis. Let's say take this and that and up to 4 and compare them side by side, right? Figure out which would be the one that might suit better. You're looking, in general, you're looking for converged solutions, okay? Not just completed solutions. Converged solutions means the criteria have been met, as opposed to just the calculation had to stop because no other shape was being able to be generated. So here's a stress plot here, as well as the different obstacles and preserves and original shape that you started from. So once you're ready, once you say, you know what, I think I'm ready to take this and produce, then you're going to create a design. So this is actually going to be watertight, solid, that you can modify further if you really want to. Or you take that into a mesh if you want to maybe create that through an additive process. So this is what I have here. So I took one of these and exported. So if you want to see how it's been built, you actually get to look at the preserves and the different shapes here. So the big plates like geometry that you see were created as obstacles. So this is built in layers, in steps, okay? And the software creates the final shape by merging all these, okay? So some very neat tools here before we run totally out of time. For example, minimum radius analysis. So if you say, well, I don't have a cutter smaller than 3/8 here, so I won't be able to get in these round corners, okay? Draft analysis. Again, is this really 2.5 axis or 3 axis, or do I have to do maybe multiple setups, or maybe create this as a a 5-axis process. Obviously, you'll get all that information right away based on the filtering, and you can make your decisions appropriately. So from here, what you do is you take that and throw in some table and vise geometry, get into the manufacturing environment, and run your toolpaths and post-process those, generate NC code, and make sure that you have what you needed there to actually produce the component. Okay, so I'm just going to do a quick NC file here using a Haas post. So anyway, sorry, I totally lost track of my time here.
Okay.
And yeah, so just to kind of clarify here, so you're going to generate the outcomes, use the pre-check. The job gets sent to the cloud. There will be some cloud credits cost associated to that, or you can get the unlimited generative design extension for Fusion 360. And then you explore the outcomes, filters, views based on properties. And once you decide you found the parts you want to process, you're going to create an outcome from them. And then what you could do is, as I was showing, create NC toolpaths in a manufacturing workspace, or run another type of analysis. Maybe I want to do some kind of fatigue analysis, for example, or export this to ANSYS Mechanical, or to an STL file to study further in Autodesk NetFab. So you have geometry that is fully usable at this point. Some resources for you if you want to explore Fusion 360 further. We are obviously available for you for consulting and training. Our contact information here, and I hope you have some questions. We have exactly 3 minutes.
Thank you very much, Dan. That was very informative. I kind of like the way you make CAM sound like just an afterthought to the whole process. Like it's
no, that was not my intention. Step. So for everyone to know,
I'm just teasing.
Any CAM questions? Louis is your expert. Okay.
So yeah, so we do have a bunch of questions. I actually have quite a few because I haven't played around with this yet. I'm really curious about how well the distinctions between 2.5D and 3D. Is when you choose 2.5D, is material being removed from two sides of the part?
Yeah, that's right. So going from, let's say, a 2-axis, which is a pure 2D cutting operation, like water jet, plasma,
sheet material, yeah.
Sheet, exactly, sheet or plate, yeah. To a 2.5, that will remove material from the opposite side to allow
that's the difference. Okay,
well, yes.
What about chamfered surfaces? Would there be any chamfers in 2.5D or not?
In general, no, but you have some options to modify the part further if you need to. If you think that maybe certain areas you might have had maybe more neat, a thicker wall, then you could take that and apply some drafts.
Okay, but then can you retest your changes to make sure you don't affect the outcome?
Yeah, definitely. You can take this into an analysis. If you actually take a generative design produced outcome into the simulation workspace, it will recognize all my boundary conditions, my loads and constraints, and you have the option to just say, yeah, okay, import them, run the analysis. Let's see now if my changes make a worse part that the algorithms have produced, or a better part.
Amazing. Okay, so the other questions we're going to have to answer offline, unfortunately. But as a closing remark, I just want to I want people to understand that all our CAM customers, our Autodesk CAM customers, and our Autodesk CAD customers, you all have access to this. You all have access to Fusion. You'll find that there's a place for it in everybody's workflows. Okay, we're not trying to displace anything, but we're trying to add more tools to your toolbox. All right, so we've run out of time. That concludes our presentation on generative design, now optimized for manufacturability. I'd like to thank again Dan Montanu, our resident expert. I invite you once again to visit the exhibitors if you haven't done so yet, and I invite you to join us right now for the last presentation on getting the most out of advanced mill turn machines using FeatureCAM. So that's it. Thank you very much, guys.